Hello, everyone. This is the Geek Nature podcast. I am your host, Kaivalya Apte, and I am back with a brand new episode on another database. This time we are talking about QuestDB, and I have Javier with me from QuestDB. So, welcome, Javier. I'm really excited to have you. Today, we are again going to dive deeper into understanding what QuestDB is, what are the use cases, high level architecture, some of the internal details, write path, read paths, and indexes, and whatnot. And yeah, so it's going to be very interesting. So stay tuned. And if you haven't subscribed yet to the channel, if you like deep tech talks, please consider subscribing. With this, Javier, welcome again. And let's start with a little bit of introduction about yourself, about a little bit about your background and how did you land at QuestDB?
Cool. Thank you very much for having me here. So I've been interested in data for a while, for the past, 10, almost 15 years. I've been working with data in a capacity or another. Before that, I was a web developer. So I always had like databases in the background, but I was never really working on data itself. But then I started working, I built a startup that didn't work, but we have to do analytics for an API. And I discovered Google BigQuery for doing like big data analytics. And then I started working more and more with things in cloud and Spark also for big data things. Little by little, I started like getting more into data, a lot of fast data with Redis. So I was, through the past 10, 15 years, I was trying virtually not every kind of data stack, but a few days ago, we were laughing at the company. There was like this modern data stack chart. And out of the tools there, I have tested maybe 200 different tools for data. So I was like working more and more with data. I was a data engineer for a while. I was helping large companies making sense of analytics and so on. And eventually, I worked as a developer advocate at AWS for a few years, specializing on data. And that exposed me to a lot of different data tools, not only on AWS, but also on the open source ecosystem. And AWS was great, but it was too big for me. I was always a startup guy, so I wanted to go back to a startup world. So I started looking for something interesting on data, and I found QuestDB. At the time, I didn't know much about them, but I liked that they were built around fast data, and they were open source. They were a small team, and it was for me the right ticket. And it's been almost 3 years since that, and I'm very happy actually that I made the change.
Awesome. Yeah. Interesting. And as you mentioned, there are like so many tools in the data space, and talking about databases, there are so many databases, and that's why we try to understand the historical context and why a certain database exists. So let's start with understanding the very basic of QuestDB. So why was QuestDB created, what it is, and a little bit about the historical context.
So QuestDB is an open source TimeSeries database. And all of those things are important because we are, first, of course, a database. We are open source, Apache 2.0 license. So you can basically use QuestDB for absolutely anything you want, no restrictions there. And we are about time series. If you try to do anything which is not around time series with QuestDB, we are not the best database by far. And I will recommend to use any other thing. But if your turn is about time series, then QuestDB it's quite important. And time series basically means that you are tracking changes over time. You get data points with a timestamp, and when things happen, it's important. It might be important because data is moving very fast. By very fast, different people mean different things. But if you are up to, millions of records per second ingestion on a database, we are happy dealing with that. Also, in time series, data tends to never stop. So eventually, in a very short time, actually, you can get to a few billion points in your database. And for a time series database or for other databases, a few billion data points is nothing. But for a conventional database, it might be a bit too much. And that's basically it. So we try to solve the problem about time series. And also your analytics usually happen around time. You want to know what happened in a slice of time, compare a slice of time with another slice of time. You want to aggregate data by time, give me the maximum, minimum, average, whatever deviation in 5 seconds chunks, things like those. So that's the thing. About the story, 10 years ago, our CTO Vlad, who is based in London, who he was working at a trading company, and they had to track assets. And at the beginning, actually, the trolling was not real time; it was batch, but it was taking too long. If I was not there at the time, but basically something that had to happen overnight could take longer than the night. So by the next morning, the process will be still running, and they have to start other things. So it was a disaster. He tried to find something fast enough to deal with data that was changing every day. And eventually, he didn't find anything that was easy to use, cheap or for free, and fast enough for what he had to do. And he started QuestDB. It started with a different name, and it was 10 years ago. And at the beginning, it was a solo project. But eventually, he started optimizing the thing. He changed companies, and he started using QuestDB in different companies. And about 5 years ago, the core team of QuestDB decided to create a company to have a dedicated team that will actually contribute to the project. As I said, we are an open source project. As of today, there are more than 100 contributors to the project. Most of them, of course, they don't work for QuestDB. Over 100 contributors. Within in the past few years, we have every few weeks a new release. And that's about the story of how it was born and why.
Awesome. I'm glad you already covered the question that I asked at the last of the episode as a last question, that what is the use case where QuestDB is not suitable? So it's pretty clear. If you're not dealing with time series data, if you're dealing with, let's say, transactional workload, probably something else like Postgres is better. But if it's time series data, I think QuestDB is really a good option. So we'll understand why it is a good option. How does it work in a bit? And coming back to the 2 points that you mentioned, right?
Yep.
So we have covered some of the time series databases and analytics database on this show. For example, ClickHouse and Victoria Metrics, and they also deal with a ton of data and time series data. You have to do analytics. And so what are the common use cases that your users use QuestDB for? Is it for analytics? Is it for, let's say, monitoring, or some other use cases?
Yeah, in our case, most of the, not most, but a big chunk of the users come from financial markets or energy or IoT data. So we see a few users doing monitoring. It's totally possible to do monitoring with QuestDB, but we are not like Prometheus, which is dedicated to monitoring, and it has like the whole ecosystem is around that use case. Or there are other time series databases that they really have a lot of tools around monitoring, and they are really specialized on that. We are not on that case. So we know some users, for example, I don't know, Yahoo has been using QuestDB for a few years for monitoring some machine learning workloads and some data and so on. But it's not the main use for QuestDB. The main use is probably, as of today, will be finance. Actually, in finance in London was where it started. But also we see a lot of energy. People like, I don't know, you need to track smart meters, production and consumption of energy, and you might have millions of users in the network, and each meter is sending maybe at regular intervals or not so regular. They are getting different data points, and you want to expose a dashboard maybe for your users, residential users. They want to know that, I don't know, they have like solar panels, for example. They want to see how much they are producing and giving back to the network. But also you need internally for aggregation. So those kind of use cases, I don't know, nuclear power plants, those kind of things. But also IoT, manufacturing in general. We see a lot of asset tracking lately with, I don't know, fleets of vehicles and things like that. So those kind of use cases are the ones we see more often. But in any case that you have data that you need to track changing over time, that will be a good thing. Also monitoring, but not especially in our case.
Interesting. So I see that all of these use cases that you mentioned, they are in a way event driven. Like there are some events that are produced every second using some IoT devices or GPS trackers or fitness devices and whatnot. So it's very interesting. So let's try to understand the high level architecture. So when I look at QuestDB, what are some of the key components that people should be aware of?
Yep. So high-level architecture is quite simple. It's one of the things we try to do at QuestDB. Wanted to be a database that it's easy to operate. So basically in QuestDB, we when you start the database, it's a single binary. That's all you have to worry about. And one thing that we have, which is a bit different from other databases, is that we tend to be smaller and we tend to use fewer resources. So you can do the same throughput with a smaller hardware in general. Of course, it really depends what you are doing, but we tend to be closer to the hardware than our databases, so you can use more machine for doing your things. So it's a single process. That's it. That process exposes different things. You can ingest data in different ways. We support the Postgres protocol. Postgres is everywhere. So the Postgres protocol, if you want, you can insert data using the Postgres protocol. But that protocol is a bit slow because it's verbose. It's not designed for real time. So we also support a different protocol, which is called ILP. It stands for the Influence Line Protocol. So we support ILP, which is more for real-time data, and it gives you faster throughput. So if you need to ingest more than a few thousand records per second, you probably want to use ILP. We also expose a RESTful API in which you can ingest data. Then we give you, in the output, you can query data, again, using the Postgres protocol, if you want, or the RESTful API. And we have a web interface, a web console, that gives you access to the SQL query, because in QuestDB, even if we are TimeSeries database, the queries are done with SQL, so you don't have to learn a new language or anything. So that's basically it. In terms of architecture, you don't really need to have a lot of things around. You can start the binary. With the binary, you can start ingesting data. You can start querying data. We have monitoring directly also. There is an endpoint that gives you metrics in Prometheus format. So if you want to plug into Prometheus, you can monitor QuestDB directly. So everything is in there. Having said so, many people prefer to have something before QuestDB. Maybe you are using Apache Kafka or Pulsar or some other kind of message broker. So if you have that, or Flink or Spark, if you have that, you can put that in front of QuestDB, and we have connectors for Flink, for Kafka, for Spark. You can ingest data directly for any of those. You don't really need it because in QuestDB, we are quite fast. So for ingestion, we can sustain fast ingestion up to some point, of course. But we can support fast ingestion without any broker in front. But some people prefer it for different things. So you can have that. In the output, you can run queries to QuestDB using any Postgres library. You can use a real-time dashboard tool like Grafana or Superset. They are two very popular choices that you can present your dashboards in QuestDB. Or you can just run interactive queries using the integrated web console. And some teams prefer to have things like Jupyter, the Python environment, to just run data science workloads or whatever. So the architecture really depends what you want to do, but QuestDB itself doesn't require anything. There is one caveat here, is if you want replication, then yes, the primary and the replica, in order to the many replicas you want to have, if you want replication, you need to configure an object store. The object store can be anything S3 compatible, so it can be Amazon S3, it can be A0 blob storage, it could be MinIO, for example, or it can be just an NFS file system. So any NFS file system. So you need to configure that if you want replication, and both the primary and the replicas need to have access to that. But that's the only thing you need to have if you want replication. Otherwise, it's a single binary and nothing else.
Okay, interesting. And so it feels like there's an entire ecosystem, how you can get data in and how you can get data out of QuestDB and, use it for monitoring, as you mentioned, for, REST API for understanding the metrics and having a SQL editor to understand what is happening. So that's very good. And as you mentioned, Postgres is everywhere. SQL is also everywhere. There is Kafka everywhere. So having a Kafka integration really helps, even Pulsar. So that's very cool. And having a single binary, it's really easy to get started with something, right? And easy to test it out. Just a little bit of understanding there. When I say single binary, is it like if I want to run it in a distributed cluster manner, is it still possible? Does QuestDB does the coordination among the various nodes of other instances that I'm running for QuestDB on its own, or there's other support required there?
Yeah, as of today, QuestDB doesn't have what I will understand typically by cluster mode in this case. So the writes, as of today, they go only to one primary. Mm-hmm. So if you want to scale out the writes, there are two strategies that users are doing for that. The first one is a bigger machine. You have a big instance, and actually with a big instance, you can go really high. In QuestDB, in an instance with, I believe, with 16 CPUs, you can ingest over 4 million records per second, of those records being like 20 columns, 10 numbers and 10 strings. So with that shape, we can ingest over 4 million, 4 point something with 16 CPUs. So you can really scale up ingestion with a single machine. In users with very demanding use cases, they do sharding. Basically, they have two different primaries and they pre-shard, but we don't wait automatically. It's in the roadmap. At some point in the future, we want to have multi-primary ingestion. But as of today, there is only one primary, and then you have multiple replicas. So the only there is not really coordination, because the only way they share data is the primary. Every time there is any change, we create write-ahead log segments, and they go to this object store that can be S3, it can be the NFS file system, and the replicas check the object store and they apply the changes locally. So there is not really coordination. You can add a replica at any point, and if the replica stops and then you start again, it will catch up from the data that is already there. So that's basically it. There is no coordination as of today. We want to have that, because this also means that as of today, each replica has the whole database. So you have the primary, you write to the primary, you replicate all the data to the replicas. Some users are asking for a distributed database, that you could have some replicas having only some shards of the data. And when you run a query, the query could be distributed across multiple servers and then get a single result. That's not how we work today. It's something that we have in the roadmap for some time in the future. But as of today, the model is similar. If you want, we don't use Postgres behind the scene, but it's similar to how Postgres works. Primary, multiple replicas, and that's about it.
Interesting. Yeah. I believe that people tend to scale up before they want to scale out.
Yep.
And it, as you mentioned, with quite a good machine for your primary, you can scale your workloads pretty well. And this is a simple architecture, right? It's simple to understand. There is no coordination happening between the cluster, and it makes it, let's say, easier to understand and easier to work with. This is what I believe.
Actually, if I can interrupt here, sorry, it actually took us a few years, because at the beginning, we didn't want to scale out. It was like, we only want to scale up, because we could see our users were very happy with that. We have right now, there are users that are ingesting, I don't know, finance brokers working across the whole Europe, ingesting maybe 300,000 records every second of the day sustainably. You can ingest faster, but in real life, we don't see people ingesting way faster than that if it's not for batch. And they do it in a single server. They don't really, you may want to have a second one for high availability. And in this case, what people usually do is double ingestion. They have some Kafka and then they ingest in parallel into two different servers. But actually, you can scale quite a bit. It was only when we started releasing an enterprise offering, a lot of enterprise was saying, oh, we need to have replication. Otherwise, we cannot pay a license. Okay, so we are going to implement replication. But when we were like purely an open source project, we like the idea of a single machine, because that way also you can stay super close to the hardware and optimize everything. The moment you have to replicate data, it's trickier to stay as close to the hardware.
Yeah, there are its own challenges. Okay, and I believe there are valid use cases for both the approaches, and it works for many use cases, so that's great to know. So just to validate the understanding here, so there's one primary node which is responsible for ingesting data, and then if you want replication, you can use an object store, let's say like S3, where you can write your data, and then the replicas, as many as you want, you can connect, and those replicas can consume the data from object store and be ready to serve the read request. Okay, so this is a pretty simple to understand architecture. I'm sure there are so many optimizations going inside that. So let's talk a bit about, the right path. So when the ingestion is happening, of course, there are multiple ways I can do. So let's say I'm a company, I use Kafka, I have some transactional workload, which is like Postgres, and then again, I use CDC, goes into Kafka. I have some data somewhere else. And there are connectors available, as you mentioned. So when something is ingested, like a real-time stream of data, what is exactly happening, right, from the API level to the storage level? And once we have the high-level understanding, we'll probably understand what kind of optimizations are done in this path.
The moment we get data, and I don't care if data is coming using the RESTful API or the ILP protocol or the PostgreSQL protocol, the first thing we have is a write-ahead log. in the write-ahead log. It's actually not the one write-ahead log. It's we have one different log per table and per connection. And in this log, it's a binary view of any change in the database. The most common change is just an append, an insert, but it could be an update, it could be create table, it could be drop a table, it could be dropping a partition of a table, changing of permissions, whatever. So any change that we do via any protocol, it goes to this write-ahead log. And then the write-ahead log, it's going to happen two things. If you have replication enabled, usually you don't, but if you have it, the write-ahead log is the part that is sent to the object store. And from that point on, the replicas and the primary, they work in the same way. So the write-ahead log, it's applied directly to the storage in the machine. So basically, once we have the write-ahead log, after we do it like very frequently, but there might be a small lag there. The lag might be, you can actually configure if you want to change things around. It's like very fast. The write-ahead log is applied, and we store everything in columnar format in QuestDB. I believe we are going to be speaking about the storage later, but if you are inserting data into a table with, let's say, 10 columns, one of them being the timestamp, we are going to store that data across 10 different files in the local file system of the machine, one file per column. So the data is going to be there. And at that moment, the data can be already be queried. Typically, since the moment you ingest the data until the data can appear in a query, we're speaking about a few milliseconds. So it's very, and that's independently of how large the data set is. And we also don't need any indexes. So the moment you ingest the data is available for querying without having to create indexes or anything like that. So that would be for storing the data. I don't know if you also want to have the view for querying the data.
Yeah, let's complete the right path. I have some questions there. Just to reiterate and to validate my understanding, whenever there is data ingestion, it is first written to a write-ahead log. It's not like single write-ahead log, but there are multiple write-ahead logs, probably per table or something. And then that write-ahead log could be also used for replication to the object store if the replication is enabled. If not, there's nothing about it, but it's mainly used for durability purpose. And then you have columnar store, which is pretty common in TimeSeries analytics database. But when the data ingestion happens, does the update of the columnar data format, it happens in memory or it is written to disk right away?
After the write-ahead log happens. In the past, when we were a non-distributed database, the path was directly from Ingestion into the columnar file binary format. But when we added replication, we implemented the write-ahead log. From that moment, first we store the data in the write-ahead log, and only after it's in the file system, it's applied in the column files.
Okay. I was trying to compare it with how things work in Postgres, because it tries to update the in-memory data structure and then, of course, the write-ahead log. And then in the background, it tries to update the data files and things like that. But in this case, it's directly updating the data files on disk. So as you mentioned, data is there to be queried and ready to be queried. So this is interesting. Now, talking about another point that you mentioned, that you don't really create indexes at this point, and the data is able to be queried or is available to be queried. So how would that work? So since the performance is one of the most important aspect, what kind of optimizations are done to make the reads faster, to make the analytics faster there?
And that's the key of QuestDB. In QuestDB, as I said, everything is around TimeSeries. So the luxury we have is that can assume many things. You mentioned before ClickHouse. ClickHouse is awesome. It's great database, excellent performance, scale to infinity, but it's a generic analytical database. Like Postgres. In Postgres, you cannot optimize for one use case because you have many different use cases. But in QuestDB, we know users will use QuestDB only for TimeSeries. And that means the data will always have a timestamp. Or you can create a data without a timestamp. If you want to do joins for lookup or something, you can create a table without that. But those tables are not super optimized because they tend to be small. But basically, the table will have always a timestamp. Most of the queries will be about a slice of time. And that slice of time will be a continuous slice of time. People want to know what happened in a period of time, maybe compared with another period, but that's the idea. So we optimize absolutely everything for that. And what we do is in QuestDB, we have the concept of the designated timestamp. Basically, when you create a table, you can have multiple timestamps if you want, multiple columns with timestamp. But one of those, you have to say, oh, this is the designated timestamp. What we are going to do is every time we write data, it's going to be in ascending order by the designated timestamp. So basically, if you send me data which is out of order, that happens very often. Before we pass from the write-ahead log file to the columnar store, we need to resort the data. But the thing is, if the data is always in chronological order, it's very easy for us to find the beginning of the file. One thing I didn't tell you, the columnar storage is also partitioned by time. When you create a table, you can configure if you want to partition by hour or day or month or week or year. So we store the data in partitions by time period. And then the data is always in columns and in ascending order. Basically, when you give me a query with a time filter, very quickly, I can prune all the partitions where I don't have to open files because I know in which partitions I'm going to have the points. Once I get to the initial partition, it's very quick for me to jump to the right, to the right timestamp. And from there on, everything is sequential. And if you read sequentially from a file, everybody's happy. The file system is going to be happy. The CPU is going to be happy. The disk drive is caching ahead of time. By storing everything by incremental timestamp, we make the common use case of reading data in a sequence just a no-brainer. That's it. I actually tell you we didn't need indexes. We support in one specific, only for one type of data, we support second level indexing, which is for, we call it a symbol. It's like an enumerated type. It's a string that behind the scenes gets converted to numbers. Can be something like, I don't know, the country code or device type or status or whatever. So you can index those columns, but in practice, you typically don't need it. We have found out that in QuestDB, it's typically faster to do a full scan if you want from the data and then filter than actually having to index the data, use more storage, and then do the second indirection when reading. So in some use cases, after you see a query that is going slow, you explain the query, you see what's going on. We recommend some users to add an index and see what happens. But in most cases, adding the index makes the query actually slower than just going by timestamp and doing a full scan.
Interesting. So I see some similarity with how DuckDB works, right? It also doesn't really have a lot of indexes. Of course, there is some support, I guess, but it is optimized for sequential scan. And if that is better, you don't really need indexes because indexes come with some overhead. And you mentioned some very interesting points. First, it is partitioned by timestamp. And then you mentioned events can come out of order, but you can always store them in a sorted order. And since these are like partitioned, you know where to look at, and then it is sorted. So you can quickly jump to the time which is in the query. I have a question on the granularity of the partition that is happening. So when you say it is partitioned by time, what is the granularity? It is, can I configure as a developer or is...
When you create a table, you configure from hour to year and anything in between. So you configure the granularity. So the smallest granularity will be per hour. And then in QuestDB, you can actually ingest data at the microsecond level. So that's the smallest timestamp and aggregation we support, microsecond. But for the partitioning, it's per hour. And it really depends how you want to use the database. You might want to create a table with one partition or another. A very common use case is maybe people have maybe hourly partitions. Your data is very frequent, but eventually maybe once a day or every few hours, you resample your data in another table. And for that other table, you choose a different unit of partitioning. So it really depends, but you have the power to configure in a table basis which partitioning you want to have.
Interesting. And probably that will also depend on what kind of queries I'm trying to run, right? If I'm running like hourly queries or let's say even daily queries, that could define my partitioning strategy.
Totally. If you have a very small granularity for partitions, let's say an hour partition, and you want to do a query spanning 2 years, then you have to open a lot of different files.
Yeah.
And it's sequential, but it's a huge number of files. 24 hours, 30 on average, not 30 on average, but 28 and something on average, days, a month, and blah, blah, blah. A lot of files. On the other hand, if you have monthly partitioning and you want to store 2 years of data, it's only 24 files times the number of columns that you are querying. It really depends how you are querying the data. You choose the partitioning that makes most sense for the most frequent queries that you're running.
Interesting. On the hourly granularity, I have a question which I've also faced in some of the scenarios and some of the use case where there are always some peak hours, or let's say, I don't know, it's a sale or something and its sale starts at 9 a.m. and then every Monday or something. So that particular hour is, really peak, and I get like ton of events as compared to other hours. So if 1 hour gets a lot of events, probably that partition will be like overloaded when you create that hourly partition. So how is that handled, and how does QuestDB make sure that does not impact the query times or even the ingestion time?
For ingestion, it doesn't have any impact at all. So one interesting thing in QuestDB is that even in a single machine, we dedicate separate resources to ingestion and reads. So when you start the machine, by default, depending on how many CPUs you have available, we decide how many CPUs we're going to be using for writing, how many CPUs for querying, how many CPUs for everything else. We have the shared pool of threads. So because in TimeSeries, it's very important to be not only fast, but more importantly, predictable. So you want to make sure no matter what, data always can be written to a database and it's always fast, even if you make a lot of queries and you are making the query engine slow. So we separate the CPUs so you can always write data quite quickly. Mm-hmm. You can also configure, if you prefer, you can configure, fine-tune how many for which things, but that's the idea. So first thing, writing data will never slow down because you have a large partition or a small partition. So when you write data, there are two things that can impact how slow can QuestDB get. Given, of course, depending on the hardware. If you have a slow drive, it's going to be slower than a fast drive. Yeah. But everything being equal, if your data is coming out of order, the write-ahead lock is going to write the data quickly. But then when we apply, we have to resort. We don't have to resort everything. We have a strategy in which we can find where data is coming out of order, and then we split the files and we put it together, and then we compat behind the scenes. But basically, data which is heavily out of order, it will have a penalty on ingestion performance. Not really on ingestion, but how quickly the data is made available for reading. Your data will be ingested fast, but then until we apply the data, you will not be able to select. And then the other part is if you are using data deduplication. In QuestDB, when you ingest data, you can configure to have the duplication directly on ingestion. It's very common on time series and on fast data to have data come in duplicate. So in QuestDB, you can configure the duplication. If you configure that, every time we get a data point, we need to figure out if it's a duplicate. Actually, we do the duplication and upsert altogether. So you can send me a data with the same timestamp and a couple of other columns with a new data point, and we don't append, we just overwrite the old version. So your data has a lot of duplicates. Or if your data is coming very out of order, ingestion will be slower, but it doesn't depend on the size of the whole data set or the partitions. So that's completely independent. Then for the read side of things, also we don't really care much if a partition is too big. If you are, of course, if you try to aggregate data in a partition which is bigger than another, it will be slower, but not because it's in a different partition, just because you are scanning more data. That's the idea. But if one partition has a smaller and the other is bigger, we don't really see the difference there. It's just about how much data you are scanning in total, how much you are processing, independently if it's in the same partition or in different partitions. So here we are not really, our tone is not really about if partitions are balanced or if they're unbalanced. It's more about how much data you need to read in one go. And then many of the operations we do in SQL, we parallelize, but we parallelize at the CPU level. It's not that we read different parts of a chunk of a file in parallel. We just read sequentially, and we are accumulating things and doing things using the parallelization, but we are not opening different chunks of a file and computing things in parallel in different parts. We don't really have the trend of skewed data for the partitions.
Interesting. You also mentioned about, since you use a columnar store, and
Yep.
there's a lot of sorting happening. And whenever I've seen a columnar store being used, one of the reasons, or one of the key reasons, is that you can actually compress that data a lot. Do you also do some sort of compression when you store the data? And if you do, then how does that impact the out of order events? Because let's say you receive an event which is for a different timestamp, and then you have to decompress that file and write it again in the sorted manner. So if that partition is huge, probably that might impact the overall latency, right?
Yep. So there are two answers here. The open source QuestDB doesn't support any compression. So
Okay.
yeah, that's about it. Bummer. And then we have also a managed version of QuestDB. We call it the QuestDB Cloud. It's just managed version of QuestDB. And we also have the enterprise version of QuestDB. Both of them use compression behind the scenes. In those cases, actually, performance is faster, because even if we have to factor in the cost of compressing and decompressing the data, since we are writing and reading fewer data because it's smaller chunks, you end up having faster performance with compression than without.
Interesting. Great. And then coming to the read part of it, it's pretty standard and simpler to understand, because you have the timestamp, because these are all time series data. You want to query and you have some start and end or something like that. And you go to that data file or partition, you read the data, you do sequential scan. Of course, you need to use modern disks that support or faster sequential scans, and then you get the data. For time series data, really the historical data doesn't change a lot, right? So, for example, assuming there are no late events or something, any data that is for 5 minutes ago, I think that is not going to change. So, do you do some caching at the read level just to make performance faster, or at least for the queries that are being made more frequently? Is there some caching involved in the read path?
No, there is actually no caching at all. The only one, QuestDB works very close to the hardware. We use direct memory mapping between the engine itself and the operating system. So that means the objects that we are reading in memory are in the same memory address that the objects in the file system. So we don't have to be converting things back and forth. So the only cache that we are using is the one that the operating system, the disk itself, is adding, but we don't really cache anything. Or because typically on time series, you want to be looking at what happened in the recent chunk of time, and that by definition is always changing. You want to be reading all the time from the recent data. So even if you are reading a query which is older, we are not caching anything there. Of course, since we are using direct memory mapping, there will be a lot of pages that are in the cache of the operating system, because if we read already the pages from disk and we didn't write or invalidate those pages, then they are still available. But that's something that the operating system does automatically. It's another thing that we like about QuestDB. If you follow the model of everything being mostly sequential and reading the recent part of data, most of the data that you're reading is already in the cache. Of course, if you're using a lot of different filters, you have high cardinality, and you filter by too many different queries, that cache will be invalidated. But very often, it's already waiting for you. But we don't have any specific query caching.
Okay. That makes sense. And the simpler the architecture, the simpler the working, the less number of configurations a developer has to make, and it makes the life easier. Coming to the replication part. So let's say I have enabled replication, and then the data goes to the object store using the write-ahead log, and then there are replica nodes available. When I read or when I make queries on the database, does it by default goes to any of the replicas, or I have to configure it to not go to the writer or the primary node and go to replica?
Yeah, so the replicas and the primary, they only share the object store. That's everything they share. So the only thing I have to do is on each machine, I have to configure via environment variable or just the server.conf file. I have to configure which is the URL or the file location for the object store. And then I have to configure which is my role, if I'm a primary or a replica. If I'm the primary, I will just have to configure like a unique cluster ID, we call it, which is to make sure things don't mix up together if you have like different things. But the idea is if you are the primary, every time there is a write-ahead lock, you just ship that lock to the object store. Then if you are a replica, you are going to be reading continuously. By default, I believe it's every second or every half a second. That's configurable. So every second or half a second, you are reading from the object store. Mm-hmm. If there is a new write-ahead lock, then you apply locally, and that's it. So you don't really have to do anything special. The data, the primary doesn't slow down if you add more replicas, because actually the primary doesn't know about the replicas. The primary only knows, oh, I'm going to put this into this object store. Maybe there are no replicas. That's fine. The primary will still put the data there. Mm-hmm. The replicas, you can have replicas. Something I do very often is I have replicas in different regions. Mm-hmm. So I may have a replica in the same region where I have the primary, and then I may have a replica on the other side of the world. So I can have lower latency, and depending on what I'm using, if I'm using a public cloud, maybe also cheaper because of network or something. So I can query data closer to the user, having multi-regional replication, but I don't need to have a line of sight between the primary and the replicas. As long as they can all share the object store, I don't have to worry about anything else. So the architecture is quite simple. We were considering different ways of implementing this, and eventually we thought this would be like, a good way of decoupling everything and making it work. The only caveat here is that if you have a replica that is very behind the primary, imagine you start a replica, you start sending that to the primary, you stop the replica, and half a year later, you start again. So the replica needs to catch up. Depending on what you are doing with your object store, data might not be there. Because you might, for example, in the managed service, we remove the data from the write-ahead lock after a few weeks. So if the replica is older than that, it will not be able to catch up. So in that case, what you have to do, you take a snapshot, a backup of the primary, you start the replica from the snapshot, and then the replica will start applying all the transactions in the write-ahead lock since the snapshot. So it's the only caveat. If the replica gets really behind, but it needs to be really behind. It needs to be like in a transaction before the oldest transaction you are keeping the write-ahead lock. So that's the only thing. But yeah, in real use cases, you don't see that. It's just when maybe you started a primary a few months ago and you're adding now your first replica. In that case, yes. In that case, you need to start from a snapshot because we don't have the whole history in the object store. But that's the only thing.
And that's probably acceptable as well because I'm spinning up a new replica. So I don't know that how much data it is it has to consume from the write-ahead log and all of that. So that probably is reasonable because I'm doing like creating a new replica. So it's totally fine. And I like this decoupling of using this object store in the middle such that the primary has no clue how many replicas are there or even there are replicas or not. And the replicas can just consume periodically from the object store and start serving the read requests. Let's say there are like, 10 replicas and geographically distribute. When I make a query, what is the component that decides which replica to use? How does that decision making happens?
Yeah, no, there is no decision making. You need to choose to which machine you are. So there is no the concept of a cluster. Okay. So if you want to query one replica, you need to go to that one. Something we are working in, and it will be available at some point, it's proper high availability in which, because as of today, if the primary goes down, you can promote any replica as the primary. The only thing you have to do, there is this environment variable or configuration that says I'm a primary and a replica. So the only thing you have to do is promote any of the replicas as the primary, but you have to do it by hand as of today. Yeah. You can automate that, but in the end, QuestDB doesn't do it for you. So you have to do it. Something we want to do is add in proper high availability, that if the primary goes down, a replica will be automatically promoted. And that's coming. That's something we want to work with. When we have that, we'll also start thinking about, because at that point, you already need to have the concept of a topology. We are implementing an object we call internally the sequencer, which is the one that knows about these things. The sequencer, as of today, already controls the sequence number of the write-ahead logs. So the sequencer will be smarter and will be the one deciding which is the primary, which is the replica, which other people are around, and so on. And at that point, we'll be able to just send data to QuestDB, and it will be automatically be sent to whichever machine. We also want to implement the same thing at some point in the future. I told you that want to be like a proper distributed query engine. We are not today. But the moment we get there, you will be able from any client just to send the query to the cluster, and the data will be coming from anywhere. As of today, every replica holds the whole database, and you need to choose from which replica you are getting data. But yeah, eventually we'll get there. We are not there at the moment.
Yeah, fair enough. And that's a valid point. Not every use case would need this, right?
Yeah.
There is always some users that will be totally fine with this model versus the other one. And simplicity, I think, is really a great thing to have. As a developer, if I have to really configure a lot of things and to make it work and to optimize it and to make it performant, that's a lot of friction. But if it's simple enough to understand, but it still works great for my use case, yeah, good enough. Great. I think you already mentioned about the fault tolerance part of it, like you have to manually promote replicas to a primary. And you also mentioned initially that some people for high availability, they configure two nodes as primary using probably the same environment variable that you talked about. And then when they consume from Kafka, it goes to automatically is replicated in real time. So you have two primaries, and then you can switch over to the primary, to the other primary. And this way, you don't have to wait for the replication to complete and to be on the same page.
That was usually before. Replication has been a thing only for the past few months, since last year, actually. But before that, the way to do high availability was double writing. It could be with Kafka or just writing directly to QuestDB. But yeah, double ingestion was the path for doing replication. The replication lag between the primary and the replica typically is a second and something. We typically check for new data every half a second, I believe, or so. So it's usually no more than 1 second and something. For most use cases, that's fine. If it's not fine, then you can have this double ingestion. And yeah, that's also supported.
Yeah. Okay. That is cool. And so as a developer, I have a choice. If I don't want to set up object store and replication that way, I can just have multiple primaries and then deal with it. And that's also fine. But talking about since you also mentioned like how behind is a replica and there are some other metrics, talking about observability, right? If I have a QuestDB running for my production workload, I want to understand what is exactly happening. And if I may need some tuning at the query level or at the ingestion level or replication level. So what kind of metrics and what kind of tuning is available as a developer?
By default, we try to have sensible defaults for everything on the database. Of course, you can fine tweak many things, but by default, we hope you don't have to. But yeah, for observability, in the same process that you start QuestDB, there is we call the HTTP minimum server, which is basically an endpoint that exposes metrics from QuestDB in Prometheus format. So you can just connect to that endpoint and you get the list of all the metrics. If you have Prometheus, then you can use Prometheus for query the endpoint. But if not, it's just a REST endpoint. You can just call it from your browser and you see all the snapshot of all the metrics. So basically there we give you things like how many bytes you are writing. If you have write amplification, which happens, for example, when data is coming out of order or duplication and you are experiencing write amplification, and ingestion can be a bit slowed down. Not ingestion, but the time to see the data. How many bytes you are reading, how many queries you have in flight. All those things are available directly exposed as Prometheus metrics. So all in together, it's like a browser page, like a screen of different metrics, and you can see like mostly what's going on there. And it's already on Prometheus format, so it's easy to consume. So actually, sometimes in QuestDB Cloud, for example, in the managed service for QuestDB, even if it's Prometheus format, then we ingest those metrics directly into QuestDB for monitoring. But some people prefer to use Prometheus because it's already part of the monitoring stack. That's why we choose that format. But yeah, that's part of you start QuestDB, it's running by default. The web interface runs in port 9000 and the metric interface in port 9003. It's right there.
Awesome. That makes sense. And having good observability metrics, something like Prometheus format is great because I can then use them and understand what is exactly happening.
And also in that same port, so in port 9003 is the health server. So it's just if you want to check a status, it gives you okay or not if there is an issue. and then 9003/metrics is actually the metrics. So we have both things in the same thing, the health check service and the metrics interface running on the same port.
Interesting. And are these metrics, probably it makes sense to expose from the primary, right? So when you say there's a REST endpoint, who is exposing this metric?
Only you can query every instance for the metrics.
Okay.
Because different instances, the thing about this is like different instances can have like different hardware. So you can be using, it's typical that my primary sometimes have more CPUs if I'm very ingestion heavy.
Yeah.
Or my primary might have fewer CPUs, but then if I have a lot of users doing queries, I want to have maybe the replicas with a lot of CPUs. And same thing, you might have a slower hard drive. You might be using like different configuration. So it might be the case that metrics are quite different on the primary and the replicas because they have like different patterns.
Awesome. I guess this has given a good understanding of the high-level architecture and what happens when you write data, what happens when you read data, how can you configure replication, what can you use. Let's talk a bit more about the future.
Sure.
What is coming? I'm sure you mentioned a few things that you want to work on. And it's an active community, so I'm happy that more development is coming soon. But what is in the roadmap?
So there are actually many different things. One thing is we were for a while just an open source database. Now we are at this point in which we are open source, but we also have a commercial offering. And there's always some tension between those two worlds. So what's part of open source? What's part of... So we've stopped right now and we say, you know what? We are going to contribute more to the open source offering. That we thought we've been contributing quite a bit. Every 3 weeks, typically there is a new release, and every release tends to be faster. But something we are doing now, we are backporting some things that were already in cloud and enterprise that didn't work in the open source. So something we are doing, for example, authentication, that is not part of QuestDB open source, is now going to open source as one of these backports. Then we are going to things that we are adding to QuestDB. We are changing, for example, the write-ahead log format. I told you we are a columnar database. That means also the write-ahead log, it also has a columnar structure. But we notice that actually in TimeSeries is very interesting because columnar structure makes sense for reading data because you might have, maybe you have 20 columns on a table. Some users have very large tables. Some users in QuestDB might have columns with 1,000 or 2,000 tables with 1,000 or 2,000 columns. That's, so having a columnar format makes sense because if you only need to query a couple of columns or 3 or 4, you have to read from there. But actually in real life, people ingesting data into QuestDB, they tend to ingest data with some information in pretty much every column. So we decided to change the write-ahead log format. And now write-ahead log is going to be ingesting in row format, but then we apply into the binary columns as columnar format. So that's one of the things that it seems like a stupid thing to do, but actually in our testing, we are getting quite an impressive performance. Ingestion is going to be higher now because we don't have to open too many files for ingesting a row. We only ingest in one file, and then we go to the columnar files. But that's one of the things. And there are a lot of small things like this that we are adding all the time. For example, just recently, one of my colleagues was playing with how to make queries that use the like operator, string like another like whatever. So when you have a pattern with wildcards and the pattern is short enough, it turns out there are some optimizations you can do at the CPU level that you can do comparisons rather than doing a loop that you compare every character with the pattern. You can actually do this in parallel in one go. So we do a lot of those small things in which like how we can improve those small parts that are interesting. So we are doing those things more user-friendly and faster. We are all the time improving performance. For example, we have on QuestDB, we use SQL, but we implement SQL extensions for time series. For example, if you want to downsample your data to aggregate your data in chunks of time, you can do select, timestamp, count from this table, sample by 13 seconds. And basically, that's going to give you the result aggregated. So until recently, sample by was not super optimized and will execute in a single thread, let's say. So now sample by has been, since latest release, has been parallelized and it's way faster. So we are doing that with a lot of operators. There are some operators that are still not taking advantage of SYND, of vectorization. So one thing we are doing is taking a look at some of those operators, make them work in parallel. We are working also on cold storage, which is when data is older than you can configure the threshold, 1 month, 1 week, 2 years, whatever, move the data out of QuestDB. As of today, you can drop partitions at any point. So you can configure lifecycle policies and drop your partitions. But if you want to remove the data from the database and still being able to query, you cannot do that. So we are implementing cold storage, which basically will remove the data from your disk, will move the data to object store like S3. The data will be in Parquet format in object store. But if you run a query that needs the data, automatically we are going to fetch the data and we give you the results from the query. As of today, you can manually move the partitions back and forth, but you cannot query a partition that you can detach a partition, move it to cold storage. But if you want to query the partition, you need to reattach again. So those things we are going to automate. So you can have a data set in which your archive, your historical is larger than your hard drive. And eventually, if you want to run one historical query a few times a month, you can just query the data and it will be automatically fetched for you and you get the results. So we're implementing that. And those are some of the things that we are working as of today. But basically, we are always thinking how to make QuestDB faster. That's we typically tend, every release tends to be faster than the release before. We tend to never release anything which is slower. For us, speed is a feature of QuestDB. So we really try hard to make QuestDB always faster, or at least as fast as the latest version if we can. So same thing, we are adding some new data types. For example, until today, we had a string data type and symbol, which is like a special string, but we didn't have a bar chart data type. And it's just like a technicality. But basically, we already released a beta version of varchar. We didn't document, but it's already actually on the binary release that, and in the source code, you can download already. But we didn't document because we are finishing optimizing some things. But basically, with varchar, we saw that you get better performance and the size of the strings is way smaller. So we keep adding new data types. We keep adding new operators that can be faster. We think how we can make like ingestion faster. We recently revamped the ingestion protocol. In the past, ingesting over ILP will be only with TCP. Now we support TCP and HTTP, which is good for transactions and so on. So we are thinking of adding our own ingestion protocol. Right now we use ILP, which was defined by Influx. It's faster than the process wire protocol, but still it has some limits. So we are thinking of creating our own binary protocol for making ingestion faster. So those are like many things that we have in the pipeline for making QuestDB. But the idea is like now making it faster. That's every optimization we do. It's faster or easier. Those are the two things that we care about, really.
Awesome. Really excited to see what's in the future for QuestDB, and I wish the whole community very good luck in releasing all these amazing features. I see performance and ease of use and also tiered storage, like you can move or automatically move data from the object store. It's pretty cool. So awesome. I think this has been a really good learning experience for me, understanding about QuestDB, how it works and different ideas. So I thank you for joining me and talking about QuestDB today. And I'm sure this is going to be a good experience for our viewers as well. So thank you. And I look forward to more collaboration on this.
Yeah, thank you, KB. And yeah, thank you. Thank you all. If you have any questions, anything you want to learn about QuestDB, we are always available on Slack. So yes, Slack, QuestDB.io, and we'll be more than happy to welcome you into our community. Yeah, thank you and have a good day.
Awesome.